Hello, this is chapter 4.7, and we will talk today about the change in basis. Often in the applications of linear algebra, we need to actually represent the same vector in two different coordinate systems. For example, computer graphic is a common example. You want to have the image on the screen, but your screen can be different. It can be big desktop or small laptop, or it can be even the cell phone screen. So the resolution is different, the size and dimension of the screen is different, but you need successfully change your image. So basically what you can do is every time you are dealing with a new screen size, you are perform the change in coordinate system. You're dealing with a new two-dimensional vector space. So how can we transform this how we can go from one coordinate system to another? Clearly, it's possible and easy because computer, you probably already today changed it 5 times. Usually, it's done by changing of basis. So you have one basis in your original vector space. You can use another one to go to one space Rn. Using the basic xc, for example, you can go to another vector space Rn, going to another basis xb, but you also can move between the two-dimensional subspaces. And we can do it by just simple multiplication of the matrix. The theorem 15 in this chapter will help you to find such matrix of transformation from one n-dimensional space to another. Let's assume that we have two different bases for the vector space V. The basis B has n vector, and basis C, of course, also have n vectors. And this is different vectors, but there is n of them. And we know that we can have an infinite number of vectors, but let's look at two systems. So then we can find a unique matrix of transformation from space B to C, such that our vector x and coordinate system C will be the product of our matrix of transformation by vector B in coordinate systems B. And this matrix is actually pretty straightforward to find. All you need to know is the coordinates of your vector B, vector you're going from, in the coordinates of the vector of the space C, the space you're going to. Okay, I realize that there is a lot of B, C's, matrices, maybe a little bit confusing. Let's just go through example and conduct the calculations. Let's look at two bases. Basis B has a vector B1 and B2, and basis C, which has vector C1 and C2. And let's find the matrix which help us to move from the basis B or coordinate system of B to coordinate system of C. Okay, let's start with a basic definition. So we need to find this matrix of transformation, which is just coordinate of our vector B in the system C, in the coordinate system C. We actually do not know this, obviously. We want to find it, but let's just give them a name. Let's call those vector x1 and x2. That would be easy to deal with. And then we don't know this x1 and x2 by the definition of the basis. We know that they are just a linear combination of our basis vectors of C, C1 and C2. And this is just coming directly from the definition for the basis. Okay, so what do we need to do is actually solve the reasonably simple system of equation. Columns of vectors C1 and C2 will form the matrix. B1 in original coordinates, we know we're given that. So all we need to do is find x1 and x2 by solving the systems of linear equation, which we've done a lot of time in this course. Okay, seems to be doable. Let's look at vector B2. Again, we don't know it, so we call it y1, y2. And again, by the definition of the basis, it's just a linear combination of our vectors from coordinate system C. Okay, so, and again, we have a systems of linear equations which we can solve. So let's just go ahead. It seems like as soon as we find this vector, we just put them together and find the matrix. Let's go ahead and solve it. And again, let's start from this first systems of linear equations. All we need to do is just write down the augmented matrix, reduce into echelon form, and we're all done. So let's just put the numbers for our vectors. So we just transfer first column as a vector C1, a vector C2 go into the second column, and our right-hand side vector B1 with the original coordinate will go to the third one. Okay, so let's conduct the row operations to find the reduced echelon form. And then whatever is in the right column is automatically give us the vector B1, the vector which we originally call x1 and x2, but now we solved it, so we have actual numbers. Okay, so we're all done with vector B1. Now let's go ahead and find the vector B2, which we need to solve another equation, but it's the same matrix equation. The right-hand side B2 is different, but the matrix is exactly the same. We can go ahead and do the same kind of calculations, but why? We can just basically augment our system with another vector. So instead of just one vector, B1 on the right-hand side, we just can put B2 right next to it. So this is our -5, -1 vector B2. And here it is now. So now when we perform a row operations to reduce into the echelon form, we apply this row operation to both vectors B1 and B2. And we will see this kind of trick when we solve two systems of equations simultaneously, pretty common at this point. Okay, so let's perform the row reduction. And this row reduction will give you actually both vectors B1 and B2. So the first row after the dashed line, 6 minus 5, will go to B1, and second row after dashed line, 4 minus 3, will go for B2. And that's the vectors B1 and B2 in the system C coordinate system. So to compile the matrix of transformation or coordinate transformation matrix, all we need to do is just write our B1 and B2 in C coordinates as the rows of the matrix, and then we set and done. And if we're given any other system, any other vectors, we can easily translate them from one system to another. Okay, now I would like you to go by the end of the chapter and practice. This is kind of, I mean, it's a tricky first couple times, but as soon as you start transferring from one system to another, it's almost became as a second nature to you. So I'd like you to practice 3-4 times to feel more comfortable.